This paper presents strategies for enhancing the performance of low-resource speech-to-text translation, leveraging pre-trained OSR models. The authors conducted experiments on both simulated and real low-resource setups, focusing on language pairs English-Portuguese and Tamasheq French. Using an encoder-decoder framework for speech translation, the findings show that a multilingual automatic speech recognition system acts as a good initialization under low-resource scenarios. Furthermore, using the CTC as an additional objective for translation during training and decoding helps to reorder the internal representations and improves the final translation. The paper's contributions include studying pre-trained multilingual OSR as initialization for low-resource speech translation with joint training and decoding with CTC objective in low-resource setups. An extensive analysis on the effect of various initializations, auxiliary objectives, hyperparameters, and amounts of fine-tuning data identifies the most important factors that contribute most to the improvements. On the low-resource Tamasheq right-pointing arrow French task, the Saint model initialized from a pre-trained multilingual OSR with only 300 hours training data achieved a 7.3 BLEU score, which is plus 1.6 points higher than the best published result from IWSLT. 22. The methodology section formally introduces the necessary terminology and describes the methods followed to train OSR and ST systems. The OSR is trained on several examples of paired speech and text from one or more seen languages. The speech translation systems are trained on pairs of input speech and target translation text, where the input speech is from an unseen language and the target translation text is from seen languages. A transformer-based encoder-decoder architecture with an additional CTC layer is used to train the OSR models. For multilingual OSR, separate vocabularies for each language are kept, resulting in a language-specific CTC layer at the output of the encoder, and language-specific input, embedding, and output layers in the decoder. Such an architecture allows for decoding tokens only in the desired target language. The models are trained with a joint CTC and attention objective function. The ST models are also based on transformer encoder-decoder architecture and are identical to the OSR models, allowing for initializing ST models with any pre-trained OSR. The ST model is trained with a joint objective function that combines the CTC and transformer decoder modules. A beam search-based joint decoding that relies on the weighted average of log likelihoods from both the CTC and transformer decoder modules is used, producing the most likely hypotheses according to the given equation. The experiments were conducted on two datasets: Tamasheq, TAQ, right-pointing arrow French, FR, from IWSLT, 22 evaluation campaign, and English, N, right-pointing arrow Portuguese, PT, from HOW2 dataset. The latter dataset is mainly used for simulating low-resource setups with various amounts of fine-tuning data. It also allows for comparing the performance against a typical end-to-end system exploiting source transcripts. Here is a combined summary of pages 3 and 4 of the research paper. The paper presents an investigation into improving low-resource speech translation by exploring various initialization strategies, fine-tuning schemes, and decoding methods. The authors utilize a multilingual automatic speech recognition (OSR) model trained on 300 hours of data from 6 languages, including French and Portuguese, to initialize speech translation (STREET) models. The OSR model is based on a standard transformer encoder-decoder architecture with a convolutional layer, followed by 12 transformer layers in the encoder and 6 in the decoder. The authors report the performance of their OSR systems in terms of word error rate, WER, and character error rate, CER, in Table 4. They find that the multilingual OSR model performs worse than the best monolingual OSR model in terms of WER, but the difference in CER is smaller. The authors also explore the effect of various initialization and fine-tuning schemes on ST models, including using a connectionist temporal classification (CTC) layer as an auxiliary objective. They find that CTC as an auxiliary objective helps across various initializations, and joint CTC decoding provides further benefits. The authors also conduct low-resource simulation experiments, where they train source language OSR models on 16.4 and 50 hours of transcribed speech and use the speech encoder from the OSR model to initialize an ST model. They find that models based on target language pre-trained OSR outperform the baseline by a decent margin in low-resource setups. The authors also experiment with various CTC weights during training and find that higher CTC weights yield better results as the amount of ST fine-tuning data increases. The paper presents a comprehensive evaluation of the proposed approaches, including a comparison with the findings of IWSLT 2022. The authors conclude that pre-trained multilingual OSR models can be a viable alternative to monolingual OSR models, and their approaches achieve a 7.3 BLEU score on the low-resource Tamasheq French dataset, outperforming prior works from IWSLT 2022. Future work includes studying the effect of multilingual ST fine-tuning and quantifying misaligned representations when initializing modules from different modalities. The authors present a comprehensive review of recent research in speech-to-text translation, highlighting key advancements, methodologies, and challenges in the field. The paper cites numerous studies that have investigated various aspects of speech-to-text translation, including jointly trained transformer models, searchable hidden intermediates, and end-to-end speech translation. The authors highlight the importance of pre-training on high-resource speech recognition to improve low-resource speech-to-text translation, as demonstrated by Bansal et al., 2019. They also discuss the benefits of self-supervised cross-lingual speech representation learning, as shown by Babu et al., 2022. The paper further explores the concept of connectionist temporal classification, CTC, and its application in autoregressive translation, as demonstrated by Yan et al., 2023. The authors also cite studies that have investigated the reordering capability in CTC-based non-autoregressive end-to-end speech translation, such as Chuang et al., 2021. The review also touches upon the topic of cascade versus direct speech translation, with studies such as Bentivogli et al., 2021, and Tran et al., 2022, highlighting the differences between the two approaches. The authors also mention the importance of jointly training speech recognition in machine translation models, as demonstrated by Zhang et al., 2022. The paper concludes by highlighting the need for further research in speech-to-text translation, particularly in low-resource languages. The authors emphasize the importance of developing more accurate and efficient models that can handle the complexities of speech-to-text translation.